limit is equal to 0. Okay? So it goes to 0. All right. So by Riemann Lebesgue lemma. All right. So by Riemann Lebesgue lemma, this integral okay, function is equal to 0. So this is 0. Okay. So this justifies that the limit of this integral is equal to the limit of this integral, because these two integral, right, the difference of these two integral is 0. Okay. Right. So that is the approximation. Okay, and okay, now we deal with the now consider this limit, okay, from 0 to pi, right? And all right, and the sign okay, look at that. Now we can split this interval from two parts. So so we have 2t f okay plus okay 0 to delta okay. So here for all delta between 0 and pi. Okay, so for all possible data. Now, in this interval, this is becomes true. So you can see that this one is an absolutely integrable function over delta and pi. Right? Delta and pi. Because t when t in between, you can replace t by delta, okay, to get the upper bound. So this is an integrable function. And again, by the, so together, this is become to 0 by Riemann the bracket. So again, by the Riemann the bracket lemma again, okay, it's 0. Okay, so we can replace the interval from 0 to pi to 0 to delta for any data, and the limit will be the same. Okay, so this is called the Riemann's localization theorem. Okay, so now we end up with an important theorem, 1.1.b, called the Riemann. So Riemann's localization theorem. All right, so let f be a periodic function with a period 2 pi, okay, and which is absolutely integrable over one period. Okay. Then the trigonometric Fourier series, all right, generated by f will converge, all right, or converge, all right, for a given x in one interval, right? So the now we are given the convergence problem. If an only condition is that for some delta greater than 0, the following limit exists. Limit n goes to infinity. Divided by 2, and the sine n plus 1/2 t divided by t and dt. Okay, so the convergence problem becomes to a justification of the existence of this limit. Okay, so this is so we have find a necessary sufficient condition for that. Okay, and you can, and from our previous discussion, delta can be, if there is one delta such that the limit exists, then for all delta in 0 and pi, such a limit exists and have the same value, okay, as we derived it before. Okay. Okay, so now we focus on the limit of this integral. All right, so to simplify our problem, so we let so fix x in and the delta in 0 to pi. All right, and we let a function t with x as parameter. Okay, so we define to be this one. Okay, so for we define a little g function, okay, as a function of t, and t is over this small cross interval from 0 to delta. Delta can be selected any value, but you can select very small. That's fine. Okay, but anyway, just like this one. Okay, so now so now the integral, right, in Riemann's localization theorem, okay, in Riemann's, there, this one becomes okay, comes to the pi delta g t x and the sine n plus 1/2 of t divided by t and dt. Okay, I forgot to put 2 divided by pi. Sorry, there. Okay, and which is an instance of the Dirichlet integral. Okay, the Dirichlet integral is something like h of t, or a function times sine alpha t and the t dt for alpha greater than 0 for an absolutely integrable function h, right, on 0 and the delta. Okay. 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 So so this is, you can see we have h is absolutely integrable over the interval from 0 to delta, and we have such a kernel. So this is a famous Dirichlet integral. Okay, and we know okay, and also we know by the Riemann Lebesgue lemma, we know that the following limit alpha t divided by t dt goes to infinity. All right, the following limit, if it exists, is the same for all delta, all right, greater than 0. All right. So we know that from the Lebesgue, Riemann-Lebesgue lemma. Okay. Because if you use bigger one, then for example, from delta to something, right? So in that range, in that interval, the integration become to 0 by the Riemann-Lebesgue lemma, as we discussed before. Okay, so for some delta, if for some delta this limit exists, then the same limit will exist for all delta greater than 0. Okay. So this is what we know. Okay, and before we do the further discussion, I want to take an example. The example suggested from the following observation. Okay, you think about most often you encounter h of t which is continuous. Okay, but when delta is go to 0, this function becomes constant if it's continuous. All right, because continuous function, all right, is absolutely integrable in any finite cross interval. Okay. And as we know, delta can be taken as small as possible. So delta can be very close to 0. All right. So this integral, all right, over a very, very tiny, even infinitesimal interval. And in that case, the h of t becomes too constant. Right? For many, if h of t is continuous. Okay, of course, if h of t is not continuous, we can still fix that. All right, but at least you can think about if this is continuous, then as delta goes to 0, very close to 0, then this is constant. So the example becomes to be important. Okay, the example is that so we let h be constant on 0 and delta. Okay, just let it constant. So i.e. h of x equal to c. All right. All right, and so we evaluate this integral. Okay, so you evaluate this integral, and alpha goes to infinity, 2c divided by pi, 0 to delta, sine alpha t divided by t. Okay, and by change of variable, we can to the alpha delta. Okay, and the sine u and the u and dt. Okay, and so where is alpha? Yeah, okay. So you can, this integral becomes to this integral. Okay, but so we have an improper Riemann integral. Okay, so this limit is equal to 2c pi and times pi over 2. Okay, so this integral, actually, this integral is equal to pi over 2. All right, so the result is equal to c. Okay, so you see that the Richards integral, as alpha goes to infinity, is equal to the constant value c here. Okay, and since the improper, the limit b goes to infinity, 0b, right? So you can see as alpha goes to infinity, this upper integration limit goes to infinity. Okay, so you can see b here, and sine u du. Okay. So this is the integral. This is actually the right. So that is the improper integral. Okay. So this improper integral can be evaluated. All right. It's equal to pi over 2. Okay. Okay. So please see. T M apostle. I think many apostle second edition, and all right. So you can see, you can find. Actually, if you use Google search, you can also know that this improper integral. Right? But if you need a textbook to know how to derive it, you can go to Apostle's textbook. Okay. So it shows you that. So this one, by change of variable, okay, you can find that this integral is equal to, as alpha goes to infinity, because delta is positive. So when alpha goes to infinity, the upper integral limit will goes to infinity. So it becomes to the improper Riemann integral, and the value is pi over 2. Okay, so you go to the C. Okay, so you have this result. All right, you have this result to know, and so you see that the localization. So it is not right. So now we have a very good result. Okay, called Dini's theorem. So that let h be a function defined on 0 and delta. Delta greater than 0. Okay. Right. All right. And because we want to have the similar result, but this is good if h of t is constant function. But h of t may not be a constant function, right? So, so now we need some condition. So if we have a right limiter at the 0, and we know that the difference, all right, divided by t is absolutely integrable over 0 and delta. Then we know then we have the limit. So the Differential limiter will okay. So the limit of the Differential integral becomes to the right limiter. Okay. All right. So next week we will show that this theorem. Right. So so I just write down the condition. So first of all, right. So the right limiter at the 0 exists, and also this function. Okay. So h of t minus the right limiter at 0 divided by t is absolutely integrable. Under this condition, then the limit of the Differential integral exists and equal to the right limiter of h function at 0. All right, and so we are very close to our goal. All right, because that this integral, because we want to evaluate the limit of this integral. The limit of this integral. Okay, so once we prove the Dini's theorem, okay, then we will find some condition on f such that this condition exists. Okay, and then we will solve our problem. Okay, all right. So this is the roadmap of the rest of this section. Okay, all right. So any questions? All right. If no, so then we will stop here.